as a former physicist. I studied astroparticle physics in grad school, specifically like dark matter and black holes as dark matter. And then after I graduated, I decided I wanted to try out machine learning and AI because it seemed to be all the rage. So now I'm a data scientist at American Tire Distributors, where we do a lot of cool machine learning and analytics stuff. And my focus there is on supply chain and logistics problems, most recently about like optimizing delivery routes and stuff. I actually have used Markov decision processes in my work there, so it's a good overlap. And in my free time, I like hiking, astronomy, and scuba diving. All right. So the outline of the talk, first, just give like a really high-level description of what a Markov decision process, or MDP, is. How to mathematically, well, I guess then we'll get into like more details, like how to quantify risk and reward, and then even more mathematical details about like all the elements that you need to set up a Markov decision process, and what's the inputs, what's the outputs, how do you describe them, and then that might be kind of theoretical, so we're going to go through like a concrete example of an MDP, and that will involve using this PyMDP toolbox package, which is like a Python package that somebody, not me, wrote to solve like simple versions of these types of problems. And reinforcement learning, which is the combination of machine learning and MDPs. So, what is a Markov decision process? So I like to bucket analytics into like three different elements, which I guess would be descriptive analytics, which is where you're kind of looking into the past and summarizing or finding patterns in what happened in the past. There is predictive analytics, which tries to use the past to forecast the future. And then there is prescriptive analytics, which is where you say, I want to be somewhere at this point in the future. How do I get there? And prescriptive analytics will tell you how to get there. So MDPs kind of combine all three of these aspects together, based on where you have been and where you want to be. They will tell you how to get there and what sort of goals rewards you'll pick up along the way, I guess. So you might already be familiar with like a kind of a more simplified version of like a full MDP, which is a decision tree. And so decision tree, the way that works is you start off somewhere, we call this the root node, and at the root node you're presented with various options for actions that you need to take. I'll just go with the example on the right. So like it's raining out. Do you go outside or do you stay in? Yes or no? And based on that decision, then you either take one branch or the other, and then you kind of go down and you're presented with another option for an action to take, and you make another decision there, and so on and so forth. And so you kind of like continue down this tree until you reach your terminal state, final state, which is the place that you want it to be, hopefully. So trees are actually like a special case of like a more general graph, which is basically just a linkage between nodes. And so you can see that the tree, there's always the root node, which is kind of special, and it branches out from the root node. With a more general graph, you could have links between any one node with any other node, and potential transitions between them. And so an MDP kind of operates in this more general sphere rather than a simplified version of decision trees. And this allows really complicated behavior in your decision-making processes, like loops. For example, you can start off in a certain certain node, and by making a sequence of actions or decisions, you could eventually end up in the same state that you started at, or maybe you could visit it multiple times. It can get complicated, but it's also very flexible and generalizable and useful. All right. So what is it more formally? It's a mathematical framework for solving sequential decision problems. And by sequential, I mean you don't just choose at one point, do I take action A or action B, and then that's it. Like, you could have to make multiple decisions, one after another, leading you to some unknown state very far in the future. And it's called a Markov decision process because it satisfies the Markov property, which is that all the states and rewards do not depend on past history. So if you're in a current state and you're trying to decide what action you want to take, it doesn't matter how you got to that state. All that matters is like what that state is, and what states you can get to from that state. So it doesn't matter about the history. And if you do have a problem that does kind of seem like it depends on your past history, usually there are like tricks that you can use to like change things around to make it so that it doesn't. The simplest trick is to just use the past as your current state. It's kind of a cheap way of doing that, but it works. And so all the inputs that you're going to have into the Markov decision process are states, actions, rewards, and transitions. And once you have all of these things defined, that sort of like defines the scenario that you have and what potential rewards you could get out of this problem you set up. And once you have all those, you can then use those to solve for two other things, which is the policy, which tells you what action you need to take when you're in a certain state. And the second thing is a value function, which tells you if you do take this action, how much reward do you expect to get from taking that action. Down here in the bottom, you can see it's kind of like the prototypical feedback loop of MDPs or reinforcement learning. We start off with an agent, which agent is just like the algorithm for solving the MDP, or you can think of it as the policy. It takes in a state and spits out an action. So like, what do you do in your current state? That action influences the environment somehow, and update causes it to update a state one step into the future, and then the agent takes that new state and decides what to do from that point on. So it goes round and round in the loop, continuously updating the states and taking actions. And there's also a reward, which kind of tells you how close you're getting to your goal. And I'll have more to say on that in a second. So let's start quantifying these things. First, we'll talk about the risk and reward and value, which are all kind of different pieces of the same thing. So the reward is fairly obvious. It's just something that you want to maximize. It could be very general. It could be whatever thing you're trying to get the most of. It could be money, it could be points in a game, Reddit karma, just like how happy you are in your life. Pretty much anything. Anything that you can put a number on and like, I want to maximize this. The risk is counter to what most people think of as risk, because risk kind of has a negative connotation. Risk in the mathematical sense is kind of like the reward that you expect to get weighted by the probability that you'll actually get it. It's literally just multiply those two numbers together. So I have a small example here, which is you roll a 6-sided die. On 2 of the sides, 1 and 4, you lose some money, $2.15. And then on the other 4 sides, you gain a little bit of money. And so the risks associated with those two, you can see it's literally just, you just multiply the two numbers together, just how much reward you expect to get. And I don't think I mentioned this before, but reward can also be negative. You can have negative rewards if something bad happens. So you multiply the reward by the probability of that reward occurring, and you get the risk. And then the value is the sum of all the risks involved. So in the example here, you just sum the two risks, 72 cents, or negative 72 cents, plus 89 cents, and you get 17 cents. And so the value of 17 cents is like, on average, if you play this game of rolling this dice, how much money do you expect to win? 17 cents. So I guess the previous slide was kind of like simplified. The example is kind of limited in its usefulness. There are a lot of other ways that could be generalized, like what if you need to plan multiple steps ahead? Right? The previous problem was kind of simple, where it was just like you roll a single die and you're done. But what if you're like going through a maze? You need to know to turn left, followed by right, followed by left, and another left, and so on. What if your rewards change with time or are random? Trying to think of a real life scenario here. Maybe you're playing a game where like flip a coin. Like even if you get heads, maybe 50% of the time you get $1, and 50% of the time you only get 50 cents or something. Or you could have random rewards that aren't fixed. There could be multiple courses of actions instead of just choosing between flip the coin or don't flip the coin. It could be like, do I go left, right, forward? You could even have like continuous action spaces. Like, say you're driving a car, for example. Turning the steering wheel would be like, do I turn it 10 degrees or 15 degrees or 20 degrees? Any angle. And then final one, which is kind of the most weird to think about, is like, what if your actions don't always result in the intended consequences? What if by taking a certain action, you could end up in any one of multiple states? You don't really know what the result of your action is going to be. So we can use MDPs to kind of take care of all this stuff. Like it's just naturally taken care of within the framework. And to do that, we need to like generalize our idea of value, so that rather than just being like the reward that we get from taking an action, it's going to be the sum of all future rewards that we get from now up until some point in the future, which could be like maybe we stop playing the game, or it could even be like infinity, far into the future. You can see from this equation, if you just ignore this gamma thing right now, but if you ignore gamma, then you can see that the value is the expectation of the sum of all the rewards. And I'll talk about the gamma later, but it's kind of like a mathematical trick to make things converge. All right, so if you have all that, how do you figure out the optimal sequence of actions to take? Use MDPs. So, getting into some of the nuts and bolts of the inputs. I have 2 slides on like the inputs that you need, and then another 2 slides on like the outputs. So the first 2 pieces that you need are states and actions. And so I'm going to take that rolling the die example from a couple slides previous and kind of just flesh that out a bit more. So let's say you have that dice rolling example as your MDP. Your states, there's a little bit of flexibility here, because you could say all of your states are like just for individual sides of the die. So like you could have a state for if you roll 1. You could end up in the state where you roll a 2. You could end up in the state where you roll a 3, and so on and so forth. But you can also choose to kind of like compactify that representation, make it like a little easier to work with. So in this case, since 2 of the sides always have the same payout and the other four sides always have the same payout. I kind of just like threw them all together into the same state because there's really no difference between them. So you can see I called the state where you roll either a 1 or a 4 S1, and the state where you roll any of the other four numbers S2. And I have kind of a graphical example over here on the right, so you can see I have like three different states. S0 is actually the state where like you haven't rolled anything yet. Like it's like the starting state. And the way that you transition between these states is obviously by taking actions. So the actions in this case are edges between the states. And in this this dice rolling game that we're playing, there's only two actions. There's either do nothing or roll, right? And so that those are the two actions that you have. And by choosing one or the other, you can transition between the states. There are only certain transitions allowed. So for example, let's say you start in state S0. If you do nothing, you just end up, you're just sitting there doing nothing. So you just end up back in the same state you started with. So that's this top loop. If you decide to roll the die, now this is a case where your action could have unintended consequences, right? Because you roll the die, but there's two potential states that you could end up in by making this choice. So you can either transition from S0 to S1, or you can transition from S0 to S2 along those green edges. And then once you're in either one of those two states, you can just do nothing, and then the scenario resets, and then you go back up to the state S0. So those are the first two pieces. The next two pieces kind of build on top of actions and states and like the transitions between them. So the first thing, like it's technically third thing, is the transition function or transition matrix in case you have discrete states. So I wish I could highlight these, but yes, you can see over here is TSSA. So this is the transition function, and you can think of it as the probability to transition from state S, your original state, to a new state, S prime, by taking action A. So you plug all three of those things in, old state, new state, and the action that you take, and this will spit out like, what's the probability of that happening. And you can see so I've kind of spelled it out for the example that we have. You can see that if you start in S0 and you take action A1, which is to roll the dice, and the probability of you ending up in state S1 is 2/6 because there's only 2 out of the 6 sides. There's also a probability that you end up in state S2 with probability 4/6. And then the reverse, going back up to state S0, you can get to S0 from any one of the states by taking the do nothing action. That's what that star means. It's wild card, you can do anything. Or you can start from anywhere. And then all the other transitions are 0. So like there's no probability, there's no way that you can get from S1 to S2. Right? There's no way that you can get from S0 to S1 if you do nothing. So those transition matrix elements will be 0. Next thing, or the final thing that you need will be your reward function. So this tells you how much reward you will get out of like doing the action or getting to the state or whatever. There's 2 different forms for it. There's this stochastic form and a deterministic form. So the stochastic form is pretty similar to the transition function. It's like a probability distribution over the rewards that you would get if you start off in state S and take action A. So start in S, take action A, maybe there's like 10 different rewards you could possibly get, and this one assigns a probability to each one of those 10 rewards. If your reward is deterministic, so like if I'm going to take take this action in this state, I'll get this reward, then you don't need to involve probability in it, and this will just be like a regular function that'll spit out the reward that you get. Okay, and then now that you've defined all four of those things, states, actions, transitions, and rewards, now you can actually, that defines the whole MDP, and now you can solve it. So just to recap, the two things that you get out as part of the solution are policy, which tells you what actions you need to take, and then the value function, which tells you how valuable your actions are or how valuable your states are. So policy here, which is usually denoted by a pi, there's also two different cases for this one, which kind of parallels the reward function. It could be either deterministic or stochastic. In the deterministic case, you just have a simple, okay, I'm in this state, what do I do? And so it just maps a state to an action. Or it could also be stochastic, which is like, okay, I'm in this state, maybe my knowledge of what's going to happen in the future isn't 100% perfect. So maybe there's like a 10% probability that I go this way and a 30% probability that I go this way and a 60% probability that I go some other way. And when you make your decision, you just kind of like sample from that probability distribution. So you can go either way. And just a note, there are many different policies for any given problem, like the MDP that describes my life. My policy could have said, don't go to work today, just stay in bed. But the optimal policy probably involves going to work. So there's many different policies, but only, I wanted to say there was only one, but there could actually be multiple optimal policies. They're all, maybe they're slightly different decisions that like lead to the same result. But there is some truly optimal policy which will optimize and maximize the reward that you're looking for. And that optimal policy, or the set of optimal policies, is usually denoted by this pi star. And then finally, the second piece that you get out of the MDP solution is the value function. And so this tells you like what sort of reward that you can expect to get from either being in a state or getting to a state, or even if you're like in a state and you have multiple actions, how much reward do you expect from taking action 1 versus action 2 versus action 3? So there's two different flavors of this. There's the state value function, VS, and also important to note that this is a function of the policy. So if you're using like a not optimal policy, then you'll get a suboptimal value function. Right? Maybe your policy is just terrible, and so your value function will be very low. But if you have an optimal policy that you're using, then your value function can be very high because you're getting a lot of reward. So yeah, there's the two flavors. There's the one that just directly maps states to values. That's just like, I'm in this state. If I follow this policy, how much reward do I expect to get? And then the other flavor is this Q, which is the action value function, or state action value function. Most people just call it the Q function. But so that maps from states and actions to rewards given the policy. So that's like, if you're in this state, how much reward do I expect from going left, going right, going forward? You just plug in different actions, and then that'll give you the reward for those, the expected future reward for those different choices. And you can see in the bottom is a kind of a callback to the original value function that I defined like five slides ago, which is that sum over discounted rewards. And so you can see this this callback to like, the value that you get out of the state is going to be sum of all the rewards that you would potentially get in the future. Okay, so that sets up all the everything, all the stuff you need to know to solve the problem. But then, how do you actually solve it? So there's actually like a million different ways to solve it, and it depends on like how complicated your problem is, whether the state space is continuous or discrete, and whether your action space is continuous or discrete. Um, all sorts of different things. But one thing that they all have in common is that they use some form of this update equation here, which is called the Bellman equation or Bellman optimality equation. And so this describes how you like update your estimate for the value of being in a state given as you like explore through an environment. This is really relevant to reinforcement learning too. So just at like a high level, on the right hand side, you can see like R, which is our reward function, and then Q, which is our value function. And then on the left, you can see the Q function again. So this is what this is saying is like the value of being in state S and taking action A is equal to like the expected value of the reward that you would get on that next time step, plus all of the rewards going forward from that point in time. You can think of it as like say you're going to take like 10 time steps. The Q on the right with the S prime and the A prime, that represents the value that you get from taking like the final 9 time steps. R represents the value that you get from taking that very first time step, and then you just add them together, and then that gives you how much value you expect to get from starting from where you currently are at the beginning. Right? So it adds that 1 time step plus the final 9 time steps. And so all of the algorithms utilize this update equation in some form or another. Various levels of complication. But we're going to go pick. I'm going to pick one of the simplest ones here, which is called value iteration, and it's the simplest one to like think about, but it's actually like a really terrible one from a computational efficiency standpoint. So you might not want to use it in practice, but the way it works is you start out with some random Q. So this is like your estimate for value of the states, and it's initially like a terrible estimate. You have no idea what's going on, and then you select a policy by maximizing the value function. So based on your current understanding, what's the best possible course of action? So you figure that out, and then you use the Bellman equation to update your estimate of Q. So even though your initial estimate was terrible, by using the Bellman equation, you can kind of make it like a little bit better. And then you just do that over and over again until convergence, until the Q value stops changing. And so even though you started at just like worst possible, totally random behavior, slowly by iteratively using this Bellman equation, you slowly made it better and better and better until eventually you've reached the optimal policy. And it's been proven that this will always work, given infinite time, of course, in some cases. So if you have a small enough problem, then you can cut it off at like a finite number of time steps, and it'll be fine. It'll be close enough. But for like really complicated problems, this will never work. But for the case that we're going to go through, it will work. Before I move on, are there any questions? Okay, cool. I think I saw someone typing questions in the chat. I haven't been looking at it, but I'll take a look at it after the talk. Okay, so now I have a slightly more complicated example that'll kind of like get into the details that we discussed previously in more detail. So the way this works is it's kind of similar to the original problem. Well, I guess it's only similar in the sense that you're rolling dice. But you have a d20 or a 20-sided die, and you're basically playing blackjack with it. You just roll it over and over again, and if you sum up the rolls as you go along. So like in the example image that I have down here, you start off at 0, and then you roll a 9. So now your score is 9, and then you roll again. You get a 6 in this case, so you end up with 15 total. And then you roll again, you get a 1, and you roll again, you get an 18. And then maybe let's say you roll again and you got like a 5, so you go over 21 and you go bust. So your score or your reward is like the numerical value of the sum of your rolls, but you can quit at any time. So like if I wanted to, once I like got to 15, I could have said like, okay, that's it. I'm going to call it. I don't want to risk going bust. So I'll just stop the game right there. And once you stop the game or go bust, you transition to this terminal state, which is like this all-absorbing state. All states lead to it eventually, and that just means like the game is over. So in the image, you can see I have 2 actions. There's the roll the dice action, or the do nothing action, stay action, I guess in this case, where you like take what you've earned so far and just leave. And the white numbers are the rewards that you get from the transitions. So you can see if you move left to right along like this top using the green arrows, you don't actually get any reward from moving along because you haven't like finished the game yet. But once you either go bust, which you can see from like the very far right side, once you go bust, you go back down the terminal state, but you get 0 reward. So you haven't gained any reward at all along that trajectory. But if you say you're in like state 16 and you decide to stay there, then the game ends, but you gain 16 points. And so your total, your total for the game is 16. Okay, does that make sense?
Yes.
Okay, so this we're going to use as like the example to figure this out. So what is the optimal strategy? All right, so now I'm going to switch over to my Jupyter notebook. Oops, no, don't look at that, that's the answer. There we go. Okay.
That's grayed out. I think you're just.
Oh, I might just be sharing the application. Stop sharing. And switch. Okay. Can you all see that?
Yep.
Jupyter notebook with stuff? Yes. Okay, cool. Good. Okay, so yeah, so you can see here it's the same illustration of our sample MDP here. And I'm going to use this PyMDP toolbox kit and like a little bit of NumPy just to handle like matrix math for like the transition functions and the reward matrix. And then also, a little bit of plotting. Got to visualize the solution. All right, so this just kind of restates the problem. You just roll until you get bust. Little more details about the states, actions, transitions, and all that. So the state space is 23-dimensional in this case. You can be in any state from 0 to 21 inclusive, so that's 22 states, plus the final terminal state. So altogether, that's 23. And the action space is 2-dimensional. It's just, do you roll the dice or do you not? And then the transition function, or in this case, it truly is a transition matrix because we have a discrete number of states. Yeah, we have that. It's mildly sparse, very similar to like the original example that we had, where a lot of the transitions are like literally impossible. Like there's no way you can go backwards from 9 to 5, or you can't go directly from 0 to 21 because there's no way to like roll 21 on a 20-sided die. So stuff like that is impossible, and those elements of the transition matrix will be 0. And then I'm going to use the value iteration algorithm, which I don't actually code up the value iteration algorithm here. That's what we're using PyMDP toolbox for. But we're going to set up everything that you need to like plug in, all the states, actions, transitions, rewards, and then you can plug that in to the PyMDP toolbox, and that'll give you the stuff that you're looking for, policy and the value function. All right, so we're first going to specify our transition matrix. So like I mentioned before, in the discrete case, it's generally a 3-dimensional tensor. So in this case, it's going to have, and remember the transition matrix maps old states, new states, and actions to like the probability of like those types of transitions occurring. So the shape of the dimensions is going to be 22, 23, 23, the same as the action state space, and then a bunch of zeros. So I don't know if I want to go through all of this in detail, but this is basically just me filling out all the elements. So like right here, you can see transition from state S to any non-terminal state S has probability 1/20, right? Because you can, like, if you start at state 0 and you roll the die, like you have an equal probability of ending up in any one of the states from 1 to 20. So this just fills in those, and then this one just takes advantage of the fact that the transition matrix is actually a probability distribution. So you can use that to figure out what the probability of going bust is, or going to the terminal state. And then the absorbing state, the final state, and then this takes into account all these stay transitions here. So like if you choose to stay, like you automatically end the game. It doesn't matter what state you're in. So that's just 100% chance that you end it. And then this is just to fix any numerical rounding problems. So let me run that, and then it's just so you can visualize it. I made the number of sides a variable, so it might be kind of overwhelming to look at all 20 at once, but like this is kind of what it looks like for 4-sided die, where the maximum number of score you can get before you bust is 5. So you can see like there's 0 chance that you can go from state 3 to state 1. Wait, is that what it is? Oh yeah, that makes sense. Yeah, there's no way you can go backwards from state 3 to state 1 because you can't roll negative numbers. So that's why everything over here is zeros. And then everything over here is 0.25s because since you're rolling a 4-sided die, there's 4%, there's 25% chance of landing on anything in the next 4 steps. Okay. And you can also see over here in the final column, there's like this is all the probabilities to end up in a terminal state. So like as you get towards the end, it's like 100% chance you're always going to end up in the terminal state, but less as you have like a lower number. And then the state transitions are pretty simple. Just automatically end the game whenever you stay. Cool. So that is the transition matrix in this case. And then the reward matrix, that one looks pretty simple. Oh yeah, so yeah, you only need to create rewards for the stay action, because if I go back up to my thing, you can see you don't accrue rewards by making rolls. You only accrue rewards by making stay actions, and like ending the game or deciding to end the game. And so the reward matrix is really simple. It's literally just like whatever state you were in at the time you decide to end the game, that's how much reward you get. All right, so you can see for this really simple case, so yeah, so if you're in state 0 and you end the game, that's really stupid of you because you get nothing. But if you like wait later and later, then as you accrue more points, then you get more reward. And then the terminal state is 0 because you can't get any reward once you're in the terminal state. Okay, and then finally the algorithm. So this kind of like covers up a whole bunch of the math, but it basically goes through the exact same policy iteration algorithm. Value iteration algorithm. See right there, value iteration. Goes through the exact same value iteration algorithm that I mentioned before, where you start off with just some totally random policy, you make it a little bit better, and then you just do that feedback loop until it finishes. So you'll see here that this is actually really really fast because it's a pretty simple problem. So it finished after 7 steps, and you can see the tolerance is like 5 decimal places. So yeah, that's it. We solved it. Congratulations, everyone. So what do we do with this now? Let's take a look. So here I'm going to plot. This is the value function. Remember there were 2 different value functions. There's the Q function, which takes state and action into account, and then there's just the V value function, which is only the state. And so this is the value function for just the state value function. And you can see it looks kind of weird. Try and do my best to explain it. I guess it starts off. Well, let's start from the right-hand side. You can see that the value of the terminal state is 0 because there's like literally nothing that you can do if you start off in the terminal state. So that makes sense. And then for like the right half of the states that aren't the terminal state, you can see they increase linearly with the index of the state, or like the sum of your rules thus far. And that makes sense because I guess it'll make more sense once we look at what the policy is, but I'll give it away. Maybe it's best if I explain both of them at the same time. So you can see from the optimal policy, it has decided that if you are at a sum of 9 or less, then you should always roll it. But if you're at a sum of 10 or more, then you should just stop and take your winnings and go home. So now in that context, let me see if I can zoom out a bit. There we go. So in that context, now the right-hand side of the value function should make a little more sense, because since the policy says that you should always stop, then whatever state you're in at this point, you're guaranteed to get that many points if you follow your policy. So that's why everything follows this dotted line on the right-hand side, because you get that many points by ending the game. On the left-hand side, you can see there's like a little inflection. And so I guess it goes downwards as your state roll. Sorry, it goes downwards as the sum of your score goes up, because once you get into this territory, there is now a potential that you could lose the game. Right? Like if you have 5 points and you roll a 20, you lost. And the closer you get to 9, the higher your chances are of losing. So that's why the value goes down. You can actually see on the very far left-hand side, it goes up just for 1 step at 1, because if you're in state 0, your score is 0, there's no way that you could possibly lose. You can roll a 20, and that's great. You get a lot of points, maybe. If you're in state 1, there's also no way you could possibly lose. So it's always favorable to roll in that case. And if you're in state 1, it's actually more favorable than being in state 0, because you're always guaranteed to not lose, and you're always guaranteed to make more points than if you started off in state 0. So that's why it goes up for that one step, and then afterward drops because you could potentially lose at that point and like lose all of your all the points that you gained. So hopefully that makes a little bit of sense. And then finally, I didn't discuss this, but this is kind of a little extra bit. So we can actually look at the state distribution, which is kind of like what is the distribution of states that you would expect to be in at any given point in time. And so maybe this is potentially confusing, but time goes vertically in this plot, starting from the top and going down. So at time 0, you can see all of the probability is concentrated over here in state 0, which is like you've literally just started the game. So that's where you are. You're in state 0. But after you roll once, now there's a 1 out of 20 chance that all of these states over here, everything from state 1 up to state 20, is populated. So this is the distribution of states that you could end up in at that point in time. And then you roll a second time, and now this is the distribution that you get. You can see now that the terminal state also has a little bit of probability of being occupied because maybe on the first roll you got like a 15. You could follow that up with a 10, and then you'd lose. So that is potentially occupied. And then you can see that like 2 is not occupied anymore because there's no way that you can roll 1 is not occupied anymore because there's no way that you can roll twice and get 1. So this kind of just describes what states you could potentially be in if you follow the optimal policy. Okay. Let me go back to my presentation. Can you guys see the presentation, or is it gray now?
I see it, Terry.
You can see it? Oh,
yeah.
Great. All right, let me full screen it. Oh, full screen. There we go. Okay. Cool. So yes, I hope you guys enjoyed that little example there. And I, just FYI, this is all going to be on my GitHub and also PyData Charlotte's GitHub. So you can just clone the repo and go through it yourself. I guess I already explained these here, but yes, this is the output that you get from the MDP. And just to recap, summarize, all the stuff that we put in there, the actions, the states, transitions, the reward functions, those are all inputs. And then finally, the 2 outputs that we got were the value function on the left and then the policy on the right. And then the state distribution, that's actually like a combination of, you can derive that from the policy and the transition function. So once you know the policy, then you can automatically get that. Okay, more complex problems. So as complex as that might have seemed, problems can get like way more complicated. So the other one was pretty simple because we could actually enumerate every single state. But in like a realistic scenario where you want to do this to optimize something in a supply chain, for example, we run into the curse of dimensionality, where that transition matrix that we discussed, because it has 2 dimensions for the state space. There's like the old state and the new state, plus the action space. It's just like a huge explosion of elements in that matrix. I just give like an example here. If you have 10 warehouses, 1,000 different types of products that all have stocking levels between 0 and 100. Now you want to plan your orders for the next couple of months. Well, your state space is going, like if you say your state space is like, I have this much product I have this much of this type of product at this warehouse. That's a 1,000,000 dimensional state space. You just multiply 10 by 1,000 by 100. And then, so your transition matrix, oh, and then also a million dimensional action space, because you need to say how much of that product you're moving to this warehouse. You get 10 to the 18 elements in your matrix, which is just ginormous. It's, there's no way that you could feasibly compute anything like that. So for systems like this, you have to resort to like approximate solutions. And this is more of an art than a science. There's a lot of tricks you could do if you want to try and can bucket all the products together. Like maybe some products are like really similar to each other. Like you're selling umbrellas, you can bucket different colors of umbrellas together because maybe people don't really care that much. You could try and get better state and action representations. So like in the very, very first example that I had with you're rolling the die and 2 sides losing money and 4 sides winning money, I had 2 different state representations. There was the one representation where every different side was its own state, but then there was also another representation which was like those 2 sides were the same state because they had the same payout, and then the other 4 sides were technically also the same state. So you can use tricks like that to try and make your state space smaller, like easier to compute. And then finally, you can use function approximation to represent the function. So this would be something like use a neural network, for example, or a linear regression, rather than using a matrix to explicitly model every single transition probability and whatnot. You can use some sort of continuous function that's parametrized by learnable parameters. So that would be another way of tackling it. The other complication, which I think I might have touched on a bit previously, was everything we talked about up to now was discrete action spaces and discrete state spaces, but you could have continuous spaces as well. So there could literally be like an infinite number, an uncountably infinite number of states and actions. And the self-driving car was, I think, an example that I mentioned earlier. You could have different continuous variable for the angle of the wheel, for the angle, or the amount of pressure that you apply to the brake, stuff like that. So those could all be continuous. And in this case, value iteration completely fails. There's no way it can handle continuous variables. So how do you handle these? Well, reinforcement learning is typically the next thing that people reach for because it combines machine learning and Markov decision processes. So you're able to learn from like very high dimensional data sets. Like the picture on the right, you can see this is the AlphaGo algorithm, which beat the world champion at Go. The state space in Go, like if you try and enumerate every single possible layout of the board, is just like astronomically high. I don't know the exact number. So there's no way that you could build a transition matrix for every single element of there. You have to use some sort of function approximation. And machine learning is like very, very good at learning patterns in these very high dimensional spaces. So that's usually the thing that people turn to. And there's a lot of like super, way more complicated algorithms that you can use as opposed to value iteration. Value iteration is literally like the simplest possible thing to do. There's all sorts of crazy things. One like a really common one is the deep Q network, which you may have heard was used to like beat specific Atari games. So the Q network works in cases where your state space might be continuous, but your action space is discrete. So it works really well for Atari, where you have like a joystick where you like move left, you move right, you move up, press A and B buttons, stuff like that. There are also other algorithms like DDPG, deep deterministic policy gradients, anything any algorithm you hear of that has the word policy gradient in it, that means that that it works in continuous action spaces, because you're kind of like taking the gradient of the action space that shows up in the update equation. And you can see on the bottom right, actor critic. That's kind of like another flavor. Actually, it's like a combination of the Q learning, the Q network, and the policy gradients. So there's like a whole plethora of different types of algorithms that you can use, and almost all of them work with neural networks. That's like where all the cutting edge research is done in this case. Oh yeah, here you can see the got some Atari examples. And I also want to point out, if you want to get started with reinforcement learning and MDPs and whatnot, you should go to OpenAI's website. They're the company that did the OpenAI 5, which was it was like an AI that could play, was it Dota, I think? Was it League of Legends? I don't remember. It was either Dota or League of Legends.
Yeah, it's Dota.
Dota. Okay, yeah, cool.
Yeah.
So they taught some reinforcement learning agents how to play Dota on a team. It was really interesting. So their whole thing is reinforcement learning. And so if you go to their website, they have like a whole bunch of they have like a library that you can use to set up your own environments. They have code to get you started in experimenting with your own algorithms. They even have kind of like a bounty list where there's like unsolved problems in reinforcement learning. And if you're able to like make some good progress on that, and like post there and say like, hey, I figured this out. I don't think they'll pay you, but you'll probably get like a really good job. Yeah, and then finally, here's just like a summary of some other things that other resources that you can look into. I got the PyMDP toolbox, OpenAI's website there. But there's also, if you want to read more about the nitty-gritty details of RL and MDPs, check out this Introduction to Reinforcement Learning, Sutton and Bardo. It's a free textbook. So if you just go to that link, it's free PDF. So yeah, that's it. Thank you, everyone.
Thank you, Eric. It's awesome.
Are there any questions? I'm sorry I went a little bit over. I'm actually surprised I didn't go further over.
Hey Eric, this is Akshata.